When people compare Linux and Windows, the usual topics come up quickly: performance, gaming, privacy, customization, software support. Battery life rarely leads the conversation, yet for laptop users it may be the most important factor of all. You can tolerate a slightly different interface. You can adapt to new software. But if your laptop dies 2 hours earlier than expected, that changes how you work, travel, and study. So what actually happens when you compare Linux and Windows battery life on the same machine? The answer is more nuanced than most people expect. In some cases, Linux dramatically improves battery longevity. In others, Windows wins by a surprising margin. And sometimes, the difference has less to do with the operating system itself and more to do with drivers, power management tuning, and manufacturer optimization. To understand why battery life differs, you have to begin with how laptops consume power. Every component draws energy: the CPU, GPU, display panel, W card, storage device, RAM, cooling fans, and background controllers. The operating system's role is to manage how aggressively those components are used. It decides how often the CPU wakes up, how high it boosts clock speeds, when devices enter low power states, how background processes behave, and how the display is controlled. Battery life is not simply about lighter equals better. It is about how effectively the OS coordinates hardware to stay in low power states as long as possible while still delivering responsiveness. Windows has one major advantage from the start: manufacturer collaboration. Most laptop manufacturers design their systems specifically with Windows in mind. They tune firmware, drivers, and power profiles to achieve specific battery targets. They test sleep states extensively under Windows. They adjust fan curves, CPU boost behavior, and display drivers to balance performance and efficiency. When you buy a laptop pre-installed with Windows, the system has likely been optimized for that configuration. Drivers are often proprietary and tuned for that specific hardware combination. The OEM might include custom power management software that integrates tightly with Windows APIS. All of this can contribute to very strong battery performance right out of the box. Linux, by contrast, often relies on open-source drivers or reverse-engineered implementations, especially for certain Wi-Fi chips, GPUs, and power controllers. While Linux has made enormous progress in hardware support, it does not always receive the same level of manufacturer-specific fine-tuning. That can lead to situations where certain components do not enter their deepest sleep states, or where CPU frequency scaling is not as aggressively optimized by default. However, the story does not end there. In many real-world comparisons, users report that Linux actually extends battery life on older machines. This seems contradictory at first. If Windows is heavily optimized by manufacturers, why would Linux sometimes do better? The answer often lies in background activity. Modern Windows installations include numerous background services: indexing, telemetry, update checks, cloud synchronization, antivirus scanning, scheduled maintenance tasks, and more. Even when idle, Windows may periodically wake the CPU for small operations. Each wake-up consumes energy. Individually, these wake-ups are tiny. Collectively, over hours, they can shorten battery life. Linux distributions, especially those configured minimally, may run fewer background tasks by default. There is typically no built-in antivirus scanning every file operation. Telemetry is minimal or non-existent in many distributions. Update checks usually occur only when triggered by the user or at predictable intervals. With fewer background interruptions, the CPU may remain in deeper idle states longer, conserving power. CPU power management plays a central role in battery performance. Modern processors support dynamic frequency scaling. They can ramp up to high clock speeds for demanding tasks and drop to very low frequencies when idle. They also support multiple C states, which represent different levels of sleep depth. The deeper the C state, the lower the power consumption, but the longer it takes to wake up. Windows and Linux both support advanced CPU scaling technologies, but their default governors differ. Linux uses CPU frequency governors such as power save, performance, and schedule, depending on the distribution. And kernel version, the default may prioritize responsiveness over efficiency, or vice versa. Windows uses its own power profiles like balanced, power saver, and high performance, with intricate integration into firmware. If Linux is not configured properly, it may use a governor that keeps the CPU at higher frequencies than necessary. This can drain battery faster. On the other hand, If tuned correctly, Linux can aggressively scale down CPU frequencies during idle time, sometimes outperforming Windows in idle power consumption. Another important factor is graphics handling. Integrated GPUs, especially from Intel and AMD, have relatively strong open-source support in Linux. For laptops relying solely on integrated graphics, Linux battery life can be excellent because drivers are mature and efficient. But on systems with hybrid graphics, where both integrated and dedicated GPUs exist, the situation becomes more complex. Windows manufacturers often implement custom switching mechanisms between integrated and dedicated GPUs. They may ensure that the high-powered GPU turns off completely when not needed. On Linux, hybrid graphics support has historically been more complicated. If the dedicated GPU does not power down properly, it can draw significant energy even when idle, drastically reducing battery life. In recent years, technologies like NVIDIA's Prime Render offload and improved power management in open-source drivers have reduced this gap, but results still vary depending on the exact hardware combination. On some gaming laptops, Windows maintains noticeably better battery life simply because the GPU switching is more tightly integrated and tested. Display power management is another overlooked area. The display is often one of the largest battery consumers. Windows drivers from manufacturers sometimes include panel self-refresh optimizations, dynamic refresh rate adjustments, and brightness algorithms tailored to the specific display model. Linux supports many of these technologies, but not always with the same proprietary fine-tuning. Storage devices also influence battery life. NVMe SSDs and SATA drives have various power states. The operating system can instruct them to enter low-power modes when idle. Windows drivers provided by OEMs may optimize these transitions carefully. Linux supports advanced power management for storage, but sometimes conservative defaults are used to avoid compatibility issues. With tuning tools, Linux users can enable more aggressive power-saving states, but this may not happen automatically. Network devices, especially W cards, can also impact battery duration. Windows often uses manufacturer-supplied drivers optimized for minimal power draw. Linux drivers, particularly for some Broadcom or Realtek chips, may not always implement the most efficient power-saving features out of the box. That said, many Intel UFI chips perform extremely well on Linux due to strong upstream support. Now here is where things become surprising. In many controlled idle tests, lightweight Linux distributions demonstrate lower idle power draw than Windows on the same hardware. When the system is sitting at the desktop with minimal activity, Linux can consume fewer watts. This suggests that under light workloads such as writing documents or reading web pages, Linux may stretch battery life longer. However, under heavy workloads like video conferencing, gaming, or compiling code, results can flip. Windows drivers sometimes extract better efficiency from hardware acceleration, especially for video decoding and encoding. If Windows leverages hardware acceleration more effectively for streaming or video playback, it may use less CPU time, indirectly saving battery. Video playback tests often produce interesting comparisons. On some systems, Windows achieves longer playback times due to optimized media pipelines and proprietary codecs tuned by manufacturers. On others, Linux matches or exceeds Windows because modern browsers and media players use efficient hardware decoding via VA-API or similar frameworks. Sleep and suspend behavior is another critical area. Windows has invested heavily in modern standby and connected standby modes. These allow laptops to enter extremely low-power states while maintaining certain background connectivity. Linux suspend functionality works well on many machines, but inconsistencies remain across hardware models. If suspend drains battery faster on Linux due to incomplete low-power state support, overall endurance during travel may appear worse. Fan behavior can also affect battery perception. If an operating system runs slightly warmer due to different power scaling policies, fans may activate more often. Fans consume power. Even small differences in thermal management can shift battery results over hours of use. There is also the matter of software choice. On Linux, users often select lightweight applications aligned with the system philosophy. On Windows, many people run heavier commercial software suites. If you compare both systems using identical cross-platform applications under identical workloads, results are more meaningful. But in everyday use, the software ecosystem influences energy consumption. Telemetry and system analytics are frequently mentioned in discussions. Windows includes diagnostic data collection processes that periodically transmit information. While these are generally lightweight, they still create occasional network and CPU activity. Linux distributions typically avoid such telemetry unless explicitly enabled. Over many hours, fewer background transmissions can slightly reduce power usage. Kernel evolution has significantly improved Linux power management in recent years. Tools like TLP, PowerTOP, and AutoKeyPuffRec allow users to monitor and optimize power behavior. With proper configuration, Linux can achieve impressive battery performance. But this tuning often requires manual intervention. Windows, in contrast, aims to deliver optimized battery performance automatically for the average consumer. This leads to a key insight. Out-of-the-box battery life may favor Windows on many modern laptops due to manufacturer optimization. But with tuning, Linux can match or sometimes exceed Windows, especially on hardware with strong open-source driver support. On older laptops, the results can be especially interesting. As Windows versions evolve, they sometimes assume newer hardware capabilities. On aging systems, background services and modern features may consume more energy relative to the machine's capabilities. Installing a lightweight Linux distribution can reduce background activity significantly, potentially improving battery longevity compared to a modern Windows installation running on outdated hardware. In controlled comparisons published by independent testers, differences are often within a margin of 5 to 15% under typical browsing workloads. In some scenarios, Linux leads by a small margin. In others, Windows does. The surprise is that neither operating system universally dominates. The outcome depends heavily on hardware model, driver maturity, and workload type. Another surprising factor is update behavior. Windows may perform background updates unpredictably, increasing CPU and disk activity. Linux typically updates when the user chooses. During an update session, power usage may spike temporarily, but it is not as persistent in the background. Over long unplugged sessions, fewer surprise update tasks can slightly improve battery consistency. It is also worth noting that some laptop vendors now ship devices with Linux pre-installed and fully optimized. Companies that officially support Linux tune firmware and drivers accordingly. On these machines, Linux battery life can rival or surpass Windows because optimization efforts are intentional rather than incidental. Ultimately, battery life comparisons between Linux and Windows are less about superiority and more about ecosystem alignment. Windows benefits from tight manufacturer partnerships and proprietary driver optimization. Linux benefits from flexibility, reduced background overhead, and the ability to customize aggressively for power savings. For users willing to tweak settings, Linux offers powerful tools to squeeze out additional efficiency. For users who prefer zero configuration, Windows may provide more predictable results on mainstream consumer laptops. The biggest misconception is that Linux automatically delivers dramatically better battery life. Sometimes it does. Sometimes it does not. The real surprise is how close the competition has become. Modern Linux kernels have closed much of the historical gap in power management. At the same time, Windows has improved idle efficiency significantly compared to older versions. In practical terms, if you install Linux on a laptop with strong Intel integrated graphics and good upstream driver support, you may see equal or better battery life compared to Windows, especially under light workloads. If you install Linux on a gaming laptop with complex hybrid graphics and proprietary power controllers, Windows may retain an advantage unless Linux is carefully configured. So which one wins? The honest answer is that it depends. On identical hardware under controlled conditions, results often fall within a surprisingly narrow range. The narrative that one system universally destroys the other in battery life does not hold up consistently in modern testing. What matters most is driver maturity, hardware compatibility, workload type, and configuration. Battery life is a product of cooperation between software and hardware. When that cooperation is strong, either operating system can deliver excellent endurance. When it is misaligned, even the most efficient kernel cannot compensate fully. The real takeaway is not that Linux or Windows definitively wins. It is that power efficiency has become a shared priority. Both ecosystems have matured. Both can deliver impressive results. And for users choosing between them, battery life is no longer a simple deciding factor but rather a variable shaped by context, hardware, and user behavior. In the end, the results surprise people not because one system crushes the other, but because the gap is often smaller than expected. and in many cases with the right hardware and tuning, Linux stands shoulder to shoulder with Windows in one of the most important metrics for modern computing: how long your laptop lasts when you unplug it.